Let's take a look at some basic estimation questions and how to do some math in your head. Why do we want to do this? Have you ever been doing homework and there's a video playing in the background and then you realize you are writing down what is being said? This is because procedural work is essentially brainless. You're not thinking, you're just transcribing. Your head is now acting like a computer data router. It's just passing the data forward from eyes to hand, whatever, and there's not a lot of thinking going on. To round up numbers, to estimate, to guess them involves thinking, and your brain becomes active. And you can tell this is happening because you become deaf. Pay attention to this. You'll be working and you suddenly realize you don't hear the background information, and you have about a second to realize you've literally gone deaf, and then boom, the sound rushes back in. This happens quite frequently on the edge of sleep. So when your brain gets really involved, it really begins to shut down erroneous outside input that's not helping. Anything that's procedural does not really require deep thinking. It's the point of a procedure is to find a routine method that allows you to dodge the uncomfortable or difficult thinking process, but the procedure can become a crutch that leaves you unable to actually think about the problem. Learning is inherently uncomfortable. Embrace it. Again, if you were in the army and they taught you how to break down and reassemble M16 machine gun, and you could do it in 30 seconds, then we tossed an AK-47 in your hands, you wouldn't know what to do. But if you'd been taught the parts of a rifle and how they generally assemble, then in a few minutes you could quickly figure out how to do it. But teaching you the procedure does not make you a discoverer. You must want to be able to do this. It's not something I can force you to do, and it takes years, much more than the hardest physics problems we have. But you learn something then. Two forms of math you've learned in your life is longhand multiplication, longhand division. How does it work? Exactly how does it work? I bet you the teacher that taught you this doesn't know. We've just passed this procedure down for many decades, and other people have invented different procedures. It doesn't teach you math, it's just a procedure to do it quickly. Let's return to the division example I just showed you, 200 divided by 7. Most of you could carry that out, but here's a question for you. Is this going to stop? Will it ever end, or is this division going to go on forever? See, the procedure won't tell you that. You just do the procedure, and you could be stuck in a loop for years if someone said, solve this, because it's not going to end. How do I know this? Well, stop thinking about the problem you're solving and think about the number. Let's not see it as division. Read it as a fraction. It's not 200 divided by 7. It's 200 sevenths. And 1/7 is an infinite repeating decimal, 0.1428571. So almost nothing divided by 7 will give you a finite decimal answer. Take a look at the bottom, the fractions 1/7 to 7/7. There's a rather interesting repetition there if you look at the pattern. There's a reason why I've long ago memorized 1/7 is 0.1428571. There's a pattern there. Do you see it? Now, how do we carry out 200 sevenths as an estimate? First thing we do is peel off a zero. We go park it in the friend zone because the zero is not going to contribute anything. If you can do 20 sevenths, then 200 sevenths means put a zero back on. I can take 20 sevenths and break it down to 14 plus 6. And this 14 divided by 7 is 2, and the 6/7, we can write it here. This is the exact answer. It is the answer. I would accept such an answer on a test. Most teachers would say, no, give it to me as a decimal, but it is truly a correct answer. If we unfriend zone the zero and stick it back on, then we get 20 and 60 sevenths. You certainly don't seem to like that. It's kind of an odd looking way to write the fraction, but it works, okay? However, if we take the knowledge that 1/7 is approximately 0.14, then isn't 2 and 6/7 really the number 3 take away 0.14? Or another way is we can pretend the 6/7 is the number 1 take away a seventh. So this is really going to be 1 minus 14. And you might go, I don't want to do it in my head. What's a dollar take away 14 cents? 86 cents. It's $2.86 is what this is. But remember, we friend zone that zero, so we put them back on. You might go, sir, that took longer than me doing longhand division with a crayon clutched in my left foot on a hot summer day on black tar, and the crayon is melting. And I could continue this metaphor forever. It's like, yeah, it takes a while to show you how to do it. But when you see a teacher just start to mumble and purse their lips together and spit out the answer, that's what we're doing. We're not doing the longhand division in our heads. We're quickly going, 207s. 207 says 27. 27 says 2 and 6 sevens. 6 sevens is take away a seventh from $3 minus 14 cents. 286. All right. And you get faster and faster and faster the more you practice it. And you impress people. What if you don't want to do sevens in your head? What if you want to just, can I round? Well, let's see. Can we round 7 to 8? Well, you try it. That's the whole point. If you try these things, then you can see if they work and you become intuitive. You can eventually say to someone, no, don't round 8 to 20. Trust me, it killed the last guy. It was, it blew up. It was a mess. How do you think engineers and scientists and doctors can look at a value and go, whoa? It's like experience, because they've tried. So if we take the exact number, we get 28.57. But if we take 200 over 8 instead, you can reduce that in your head quickly. 50 over 2, it's 25. Well, if we compare these two numbers like they're a test score, we get 87% correct. This means 7 and 8, who have an exact ratio of 0.875, it's not a surprise. You've made a change of two numbers that put them about 13% apart, and the answer you get is about 13% apart. Now, we can improve this estimate by a little trick. If I try to figure out what an eighth is, which is really easy, I'll start with a half. That's a quarter, so an eighth is half of a quarter. So 50 cents, 25 cents, 12 and a half cents. An eighth is about 12% of a number, and a seventh is about 14% of a number. So by turning 7 to 8, I've committed about a 2% error. So that means I've increased the bottom by 2%. So what if I changed the top by 2%? What if I altered the top to compensate for that? So 2% of 200 would be 4. So that means I should have boosted it by 4. So my 25 becomes 29. Yeah, that's darn close. So that's one way of upping the estimate. I call this counter rounding. You round one number down and then you round the other one in the same direction, and it usually cancels. Let's take a look at another one. A car travels 333 meters in 7 seconds. What is its speed? This would be what we want written on a test. Formula, values, answer. Could you estimate this instead? Well, let's see. First of all, changing 7 to 8 now doesn't help. You can't do that math in your head any more than you could do it in its original form. But if I round the 7 to 6, I can reduce that fraction to 111 over 2, and I get 55.5. And you might go, well, I can't do that in my head. Yes, you can. $111 split between two people. Well, it's 50, and it's 5, and then, and the other one split. Turn it to money, and you'll do it instantly, guaranteed. So this also turned out to be about an 86% accurate rounding. What if we counter round? I lower the bottom to 7, so I lower the top as well. And maybe the fact that I lowered both numbers would stop the error in the rounding. Well, let's see. 300 over 6 gives us 50. Holy moly, is that close now? So that's a quick example of counter rounding. We could pull another kind of rounding. What if you just, I let you change 333 to 350? Well, you can reduce that fraction quite easily in your head, and you get 50. And again, when this is spread out and you're allowed to see it all and it's explained, it takes vastly longer than your calculator. But once you get the notion of doing this, you can go in your head. So what you can do is set up the problem like you see at the top right of the screen here. And just before you hit equals on your calculator, carry out the estimate in your head. Just go, 333 over 7. It's going to be more than 33. 333. Oh, 350 over 7. It's 50. And then you go like, oh my gosh, I'm smart. So try. Doesn't hurt. Just pause for a moment before you hit equals. Now, what is wrong with me and the number 7? Why am I so obsessed with 7? Well, Isaac Newton was, so shut up. Isaac Newton thought there were 7 colors in the rainbow, and I spent my youth feeling stupid because I could not see 7 colors. He picked 7 colors because it's a magic number, and there are 7 notes on the piano scale. Right? We have 7 colors in an octave. So C, D, A, B, C, D, E, F, G, A. A to G is 7 notes, and he was like, 7 notes, 7 colors, woo, magic. Yes, Newton was a bit of a mystic. If I line up all the fractions that exist, 1/2 to 1/9, all right, I know there are others, but seriously, who knows what 1/17 is? If I line these main ones up here, there's a pattern between them. To do 1/2 to 1/4 to 1/8, if you know a half is this, then you're just treating it as 50 cents, 25 cents, 12.5 cents. If 1/3 is 33 cents, then a sixth is half of it. Half of 33 cents is 16 and it's 0.6 cents. A ninth is a third of a third. So 33 cents split 3 more ways into nines, you get 0.11. And 1/5 and 1/10 are also tied to each other, 0.1 to 0.2. It's only the 7th that's sitting out there without any friends is the only fraction that you can't arrive at by using 1/2, 1/3, or 1/5. So if you know 1/3, 1/2, 1/5, you know 9 of the 10 primary fractions, or 8 of the 9. Then they add the 1/7 to it, and you've got all sorts of excellent predictive power. And the fact that 1/7 is 0.1428, take a look at those digits again. There's something really magic there. This little chart here would go a long way into you estimating numbers in your head.